Hello, everybody. Welcome to our seminar, ML at HZG, the 23rd episode. Today we'll be talking about neural differential equations for mixology. We have one main paper for the session today, capturing missing physics and climate model parameterizations using differential equations. For those of you who've already looked into the paper, it's a fairly quick read. I'm going to spend about the first half of my slides on the main paper, just trying to get across what is happening here. It's very related to what we had last sessions, I think, in the last session. And for those who are interested, then there's an underlying paper, Universal Differential Equations for Scientific Machine Learning, from the same group. Which is going a bit more about the details regarding the underlying mathematics of the gradients, how to compute them, and a bit about the programming and the programming environment. I'm going to make a break between the two papers, and then people can make up their minds if they want to sit with the second half. I hope that the first half is going to give you a rough idea of what's going on. So just getting back to last session. Last session we had already a session on parametrizations, in that case for cloud microphysical processes, where we had a big system that was expensive to run, but we also were given some lower dimensional system. I think it was 4 sets of equations here. I'm just showing the first two. So we had the dynamics, we had the equations, the shape of the equations, like the structure, but what we were missing were a few of the terms on the right-hand side of the differential equations. And we wanted to use machine learning to give us these, to predict these terms from a few regressors. The authors, Axel Seifert, who presented last time, and Stefan Rast, we trained a neural network to from a list of different predictors, get a neural network to get these values themselves with mean squared error. Then they would be plugged into the right-hand side of the differential equation, and then they would integrate the systems that they learned this way. What was a bit disappointing here is that even though while it seemed like they would get the terms themselves very well, some of them from the machine learning model, when they actually looked at the solutions and they integrated the differential equations, they saw that there were substantial differences between the solutions they got from their learned differential equations versus those that they were supposed to get from the full model without the parameterization. So there was a bit of a disappointment where it wasn't entirely clear where that came from. And one of the things that I think we quickly mentioned at the end of that session is that maybe it's because the loss in the space of the right-hand side of the differential equation, over which we actually minimize the network, isn't necessarily a very good predictor for the performance in the space of the solutions. So the paper we're going to talk about today is going a bit more in that direction. Let me quickly check if my connection is still running. So I'm streaming from home today. Can anybody say anything so that I can hear them?
You're fine, Marcel. You're great.
Okay, thanks. So the application today is not about super droplets. It's about ocean simulations. The simulator we're looking at is Oceananigans, which implements the Boussinesq equations on rectangular domains. So here we see a snapshot of, I think, in 256 by 256 by 256 cube. The simulation setup is that of a big cube of water that has different prognostic variables like velocity and temperature. The thing that we're interested here in the setup is the temperature. At the very initial state, you can see this here on the right-hand side, we have this profile of temperature as a linear gradient from a warm top of the cube that then gets slowly linearly colder as we go down to the bottom. The special thing about this setup is that there is heat loss at the top, so there's cooling. So what happens over time, time here on the right-hand side plot is given with different colors, is that we can see that over time the surface of the water cube cools. But what is interesting is that this cooling at the very surface level of the water cube doesn't just result in linear temperature gradient just with change slope, but what happens is that we have this whole section of the water cube which cools pretty much at the same speed as the very top does before we have this particular layer that is forming and is also moving downwards over time, where the temperatures change rather quickly before we go into the deep parts, which stay pretty much unperturbed. So the interesting thing here is two things. First of all, we have this three-dimensional simulated system with all of these prognostic variables. But as you can maybe already appreciate from the left figure, in terms of temperature, what's really interesting is going on is along the z-axis. So just spatially averaging along the horizontal directions gives us already a lot of idea of what is going on in the system. In fact, these two images on the right that I've been using to explain what's going on here are exactly that. They're horizontally averaged system states. And the other thing that's interesting here is that, as we've seen here, this horizontal profile, sorry, not the horizontal profile, the vertical profile of the temperature, it has some interesting dynamics. The mixture layer moves over time. Also, the shape changes. So there's something interesting going on just on this horizontally averaged temperature profile. And similar to last time, where we already started out with the right shape of the differential equation, we were just missing the numerical values for some of these terms. This time we also have a differential equation that describes how these temperature profiles evolve over time. But there's again a term missing. In this case, the term is the turbulent vertical heat flux. It's not explicitly given in today's paper, but just from the description, I try to reconstruct how it's probably computed. So it's involving velocities, a velocity component, and the temperature. And there's a double integral, which can be annoying, but the most annoying part for us at this point is that we, in order to compute this quantity, which has here a bar on top, which in this paper means it's horizontally averaged, so it's just along the z-axis, is that we, in order to compute it, we need reference to the full system state, which is three-dimensional in space and also evolving over time. So we need to run the full simulations in order to be able to describe the dynamics of this one-dimensional system moving forward in time. So just like last time, what the target will be is to estimate this quantity, to predict it from some of the quantities that we have access to. And since we would ideally like to run this low-dimensional system, just this one-dimensional spatial system, without reference to the full system state and on its own, without having to keep track of velocities, we just want to predict the turbulent vertical heat flux from the horizontally averaged temperature profile, of which we want to describe the dynamics of. Okay, sorry. Asking quickly again if everybody's here.
Yeah.
Okay. Sorry for this. I'm on a public Wi-Fi, which asked me to log in again every 2 hours, which is a bit annoying. Okay. So from the embedding of the neural network that we want to predict this term here, we can either appreciate the fact that the neural network is embedded in a differential equation, which we will come to in a later point, or we can read out from this differential equation what this neural network is supposed to do. And if we compare like what's going in, what's going out, we can identify a classical vector-to-vector regression problem where the neural network maps numbers from the reals to the power of n+1, so n+1 dimensional space, where n is the number of discretized z levels along the z-axis, into another vector of the same size. So what goes in is the horizontally averaged temperature at each of the z levels, and a single number, which is the speed at which temperature is lost at the surface of our cube. And what we're trying to predict is this target quantity, the turbulent heat flux. And this one, I'm not entirely sure why it has one more dimension than just the horizontally averaged temperature. I guess it's because some half-level stuff is happening. From a machine learning perspective, this is, however, just a minor detail. We have a vector-to-vector regression problem. If we have the inputs and the outputs, and we accumulate a lot of data points for either of them, we can just have a very simple neural network. In this case, it's just 3 layers with Rayleigh units that maps the inputs onto the outputs. So the neural network that we're looking at is 3 fully collected layers. One could have argued maybe along the spatial dimension, there might be a lot of structure. You could go with, say, 1D convolutions. But this is such a low dimensional, simple problem for mapping that this really is a rather basic toy network that's not going to be of much focus here for us. It just does its job. What's much more interesting is how do we actually train a neural network? And there's 2 ways that they're approaching in the paper. The first way I already alluded to is you just see this as a vector-to-vector regression problem that we also looked at in the last session, the type of learning, training these networks. The second one would be to really appreciate that, that this neural network is embedded within a differential equation. So starting with the direct approach, the regression approach, we have these full numerical simulations. What we would do is we would extract the full spatial temporal profiles for the temperature and the velocities and compute the horizontally averaged quantities from that. And once we have that, we can just write down a mean squared loss, where for every time point or that we extracted from the simulation where we computed these quantities from, we just do the targets minus what's coming out of the neural network, and we try to minimize this difference with mean squared error and the gradients of the neural network, which we get because the neural network is usually written in an auto-diff environment. And then what comes out of this is predictions of the neural network that look like this. So these are these quantities, these target quantities. Here, the dot I try to, instead of z, I try to indicate that we're doing this for all the z levels at the same time. I'm not sure if you're familiar with this notation, but it's just supposed to indicate that this thing here is for each given time point. This is a full vector. And this norm here would be the Euclidean norm. Anyways, for any individual time point, so these are full vectors, we can here show the values of this as a function of the depth for the turbulent heat flux, and the full lines are actually out of the full 3D simulation computed through spatial averaging, and then the dashed lines is what the network would predict. There's one caveat here, which is that the network isn't, that I'm showing here in this figure, isn't purely trained with this loss. It's also trained with the other loss I'm going to present in a second. But this is roughly what we can expect the network to do. You see, it's a very simple network. So it's trained also with mean squared error. So it produces rather smooth predictions, doesn't really follow all of this very fine detailed structure, but it's doing a decent job at predicting what's happening. It's just that last session, we already saw that doing a decent job at predicting the missing parts of the differential equation doesn't necessarily translate into particularly good solutions of the differential equation. So that brings me to the second way of training this, where I already said we can appreciate that this neural network is embedded in a differential equation. And in order to do this, we can define a loss that can again be the Euclidean norm. We can define a loss directly on the solutions of the differential equation. So if we extract the temperatures from the full simulation and we do the horizontal averaging, then the idea is that this will have evolved according to the ground truth dynamics, assuming for now that this is actually a good description of how this quality evolves over time, which I didn't check. And we can compare this to a second simulation, a rollout starting from the same initial state, which evolves according to the dynamics which we learned. So you would solve the system as an initial value problem with the dynamics that we learned with the neural network from the same initial state, and you would get a full trajectory over space and time. And then you do the error on this. So what this would look like in this case is this figure I already showed. I'll just investigate it with a bit more detail. Is for different time points, we get these different profiles. And this notation here, where I have the dot on both sides, is supposed to show that we do this for all the different Z levels, but also all the different times. So the loss that we would be trying to minimize is really all of these dashed curves which come out of the network, and the difference to all of these non-dashed curves which come out of the simulator. And we're trying to minimize the error simultaneously for all of those. The difference here is that especially if you go to longer time points, if you're making an error on the right-hand side of the differential equation which involves the neural network, if you integrate for longer, these errors are really going to accumulate. And while this type of loss ensures that you get the right-hand side correctly, it essentially only guarantees that you do a decent job at a very first Euler type integration step. It doesn't show you anything about how errors accumulate on the long run. Now, of course, if you have a perfect right-hand side with zero error, then you're guaranteed that also the full simulated trajectories are going to be good. But in practice, you never have zero errors, and you don't know if the errors on the right-hand side are going to accumulate or not. While with this type of loss, you already did the integration, and then if you do the mean squared error on the solution, you can directly see this. So this now would really correspond to what we argued last time. Would be really nice is to have a loss that punishes these differences between the machine learning solution here in this plot in blue and the real solution, which here was in black. And this is what is actually happening. So the axis is kind of flipped, but this is really trained on a loss that punishes the differences between these lines directly. So yeah, this is the main part here of this paper, the cool thing that they did, and this is the result. Unfortunately, as I said, they don't really separate the results for just training with one loss versus both losses. So I can't really quantitatively show you that this is really what's solving it. I'm just saying this has been done and this is possible. And it's not so difficult. The one thing that you really need in order to be able to do this, to directly optimize over the solutions of the differential equation, if the differential equation is given by a neural network, you need to differentiate, you need to be able to differentiate the solution of the numerical solver with respect to the parameters of the network, which I here made more explicit. And this is described in the second paper of today, which we're going to look at in a second. But I want to make a quick break here, take some questions and let people decide if they want to stay for the second. But so just to iterate, so mostly last session, we've already learned that learning differential equations by directly targeting the right-hand side can be dangerous. We do care for the solution, not for the right-hand side per se usually. And losses on the right-hand side can be small, but errors on the solutions can be big, as we've seen last time. And this time we've seen that we can learn differential equations via directly optimizing the solutions if we can differentiate through the numerical solvers. And this if is what the second paper is going to deal with. How do we do this? It turns out it's not that difficult. A lot of the framework that we use for training deep neural networks can actually be used, repurposed fairly simply. if you're not too interested in the details, I can give you the high level conceptual summary. It's just chain rule, it just works. Is anybody still here and can hear me, and do we have questions?
Yes, in fact, we do have questions from the chat. Felix Stila from DKRZ asks, regression to the mean seems to play a big role in the kinds of errors that are emerging, which is no surprise given that the networks are trained with MSE. With NDE, I guess that would be density estimation. Could there be a way to ditch MSE losses entirely for something less biased, or did I get something wrong? Because I thought the errors were quite small, actually. What do you think, Marcel?
So there's different notions here. The one is, what kind of loss do we have? And for simplicity, people usually go for regression problems for unbounded continuous output variables. You usually go for mean squared error simply for simplicity, in the sense that mean squared error of 0 between two things means that they're identical and you're done. You're predicting what you're supposed to predict. And larger errors are punished more. You could go with a lasso error, an L1 loss, or adversarial losses. This is all true. The thing I wanted to stress more is not the kind of loss that you're doing. That's the same for both of these loss types that I showed, right? It's both Euclidean error here, even though here, I must admit, I forgot the square. These are both the same types of losses. What's much more interesting, at least my takeaway from these papers, is what is the space over which these losses are taken. One is the right-hand side of the differential equation, which then goes into a numerical solver. And one is the solution itself. And I think one simple example where we can really see the difference is if we imagine just a one-dimensional autoregressive system where the next state is some alpha times the current state. And let's say the ground truth alpha is very, very close to 1, so stability, but slightly smaller, say 0.999. And then you have two estimates for alpha. One is clearly smaller, say 0.9. That's quite a lot away from the ground truth. And then you have one which is much, much closer in a mean squared sense in that space of right-hand side of differential equation, which today is 1.01, right? That's much closer. But if you do the integration of these systems, even though one of them, the right-hand side in mean squared error sense, is much, much closer, you're going to find that the second one is unstable. There's going to be a very, very striking difference in the solutions that you don't want to have, that you only see after you've integrated for a bunch of time steps. You don't see this directly on the instantaneous tendencies. This is what I wanted to stress. Whether it's mean squared error or L1 loss or adversarial stuff or any other funky stuff that you want to use, this can be added on top of that and changed. Yeah, maybe mean squared error also for the solutions isn't necessarily what you want to go for. If you have rich structure and you don't just have one-dimensional profiles, but you have 2D stuff which has a certain texture to it, yeah, you can of course add adversarial losses to the output of your integrated simulator that you learned. So did that answer your question somewhat?
I thought it was a good answer. I don't know, Felix, if you want to follow up. In the meantime, I have maybe a sort of related question, which I think Felix says in the chat, yes, it does answer the question. So, Marcel, you mentioned the idea of errors accumulating. And that seemed to be the case in the super droplet paper we looked at. It's the case in a lot of other situations as well. I'm wondering if it's really the case here. It seems that they're simulating a big block of water which gets cooled on the top in the middle, and then this disk of cold water falls down. And yeah, this leads to all these ripples and eddies and turbulent behavior, but in the long term, the dynamics are stable. Certainly at the spatial scale where the neural network would be operating, right, where you remove all horizontal space and you reduce everything to just a vertical coordinate, it seems like the dynamics are actually quite stable there. So that even if it's almost like the opposite of the previous paper we looked at 2 weeks ago, where now even if you make mistakes in the ODEs, you're quite likely to get the right answer in the equilibrium states.
I can't really comment on this. I would really like to, either because I'm lacking the intuition, but what I'm just trying to point out, which I think I quickly mentioned while explaining it, all the results in the paper are with neural networks that are trained on the rollouts. So they see their long-term errors. So this whole point of, if we only do train like the right-hand side of the differential equation, the instantaneous changes, we would also be guaranteed to get something stable. In this case, I can't answer it. I would really like to have seen that they only train the network with the first type of loss, and then see these long-term things. I would imagine that 0 hours and 18 hours look really good, but then maybe 6 days start looking really bad. I can't say that. This would be my intuition, but this is in the current form of the paper as it is published on arXiv and preprint server. It's not in there. It might be done in the full version of the paper. Or did I get you?
I think you answered that question. Yeah, yeah. I mean, yes, it's hard to know without turning each of these tricks on and off, doing what they call an ablation study to know exactly what's important here.
Okay.
Yeah, I agree completely. I would add one more observation. I don't know, maybe we have time for 1 or 2 more questions if anyone else has. But my other thing that struck me is that they train it cooling the surface at 25 watts or 75 watts. I'm guessing this is actually watts per square meter. And then they test it on 50 and 100, and 50 makes sense that, you want to test it on some condition that wasn't in the training data. You want to show that you can generalize if this is going to be useful. But 100 really seem to be making this problem more difficult for themselves. They don't just want to go to new conditions. They want to go outside the training data in amplitude. So it's cool that it worked. I wondered why they did that.
Yeah, it's cool, and it's usually not guaranteed with these black box neural networks that they extrapolate outside of the training regime.
Yeah.
It might be that the network is so shallow and that the dependency is in fact linear, that they kind of get that through the architecture of the network, but I'm not sure. Probably not right away. So it's a really cool and interesting result, actually.
It is. I find a little bit of a shame that they have this amazing software stack, which I guess you're about to talk to next about you can differentiate through differential equations and all this amazing stuff. But if I'm understanding right, they only really have to differentiate through this linear term in order to train their neural network, the diffusion term.
Yes, the stuff that they need to, the stuff that they need to differentiate on top of the neural network, which they already needed to differentiate just for the basic vector to vector regression type training, is these operations like the spatial derivative and of the network output, and the second, if you take these things together, the second spatial derivative of the network input. These are the two things. So it's not something that you couldn't implement, say, in PyTorch with, I think, two convolutions, maybe. So it's not yet the full showcase of all the cool things, but it does apparently come out of their framework for free, that you don't need to manually code down these extra terms. But yeah, this is something I might be talking a bit more in detail in the next part.
Okay, thanks. That's all I've got.
Okay, so if then there are no more questions, then I would start with the next part. So the next paper, it's actually a very broad paper in scope. I think it's summarizing a lot of work of the group that has been going on there for probably several years. And you also see there's a few authors on there. So if you looked into it, you might have noticed it reads mainly as a showcase for their SciML package, trying to explain all the cool things that are in there, which might be difficult to understand why they're cool in there. At least it was what it was like for me in the beginning, and on some of the details still is. We're not going to be too concerned with that, though. I'd like to quickly come back to that at the very end. You might also have seen that there is a treatment of the parametrization that we have in today's main paper about this, this cube of water in section 4.1. So if you were interested about understanding a bit more the preliminaries of what's been in today's rather short paper, you can also have a look there. We're mostly going to be concerned with chapter 1 there, because it's kind of laying out the groundwork. And the main idea is to augment known differential equations with machine learning models. So with known differential equations, in their notation in this paper here, they write down this F, known dynamics. With this, we mean stuff like we had here. Like you have the right-hand side of the differential equation, like its overall structure. The fact that to the output, this quantity that is output by the neural network, you apply the spatial derivative, and that you subtract the second spatial derivative of this kind of structure. This would be the known dynamics, which come from first principles, but there are also then some unknown effects that you want to learn in a data-driven way, where data can be either simulations, as we've had it here, numerical simulations. In fact, actually, they could even be actual observations, I claim. Like you can learn a dynamical system where F is your climate model of choice, in fact, and then you can learn some terms, corrective terms, that you want to include in the differential equation to make the solution of the combined system, they call this a universal differential equation. So to make sure that the solution, the numerical solution of these dynamics are as close to data, as I call it here, colloquially, in some sense. Again, could be L1 loss, L2 loss, or some other stuff like adversarial losses. So that's the general idea here, slightly more abstract than the last paper. You combine something with some black box machine learning model. I kind of like that they spell out for us. It doesn't have to be a neural network. It can also be a random forest, or in principle also a Gaussian process. Anything that you can have gradients for. So gradients of their inputs, of their outputs with respect to their parameters. One caveat about this grand vision of just having corrective data-driven terms for your favorite geophysics models is that the F, as David pointed out in his last question, the F has to be either written in a auto-differentiation environment, such as the SciML package, or also PyTorch in principle. Or you have to manually provide the gradients. I know for PyTorch, you can actually write hooks where you can explicitly tell it, like from this function F, this is the gradients. And then you don't need to have F written in PyTorch itself. I mentioned that for other stuff like Julia, that package, this stuff also exists. So this is the caveat. You would need to rewrite the stuff that you already have from physics in such an environment. But this is one of the appeals of this Oceananigans simulator. They have written this in an environment where it can interact with auto differentiation. Okay, so that's the main idea. Again, learn parts of differential equations such that the solutions have some optimal under some loss. The underlying thing, as I already kind of spoiled a bit, is the underlying workhorse is simply the chain rule in multiple variables, multivariate chain rule. As a quick refresher, so these equations are just copied from the first chapter. This is their notation also. if you have a function of some input x, let the output you denote that as y, and f consists of a concatenation of several functions. So if you apply f to x, the first thing you do is you apply f1, and then the output you apply to f2, and all the way up to fl, the last one. Then for its Jacobian, which is the matrix of all the partial derivatives of the outputs with respect to all of the inputs, for the full combined function, it's just a product of the Jacobians for the individual functions. So this is the if function from up here, and the derivative with respect to its input, where its input is computed in this forward fashion up to that layer, well, in this case, the previous layer. So what this says is you can get the Jacobian for the combined thing by multiplying the Jacobian matrices for the individual things. They wrote it down in this form with the vector matrix products of some vector v with all these initially confusing brackets, because this is also really important for speed. Reverse mode differentiation is what it's called if you do it this way, where a vector matrix product gives you, again, a vector inside of the innermost brackets, which then gives you another vector matrix product. So you always, as you go backward in time, so you start with the last Jacobian actually, you always only need to store vectors in memory. You never need to do a matrix-matrix multiplication. That makes it really fast. So these are just some cool properties of chain rule that are very, very, very explicitly used in machine learning, especially in deep learning. In all of these frameworks, PyTorch, TensorFlow, Theano, yeah. And they're also standard lingo. So this thing here, where we go forward from the original input up to the IF layer, is called the forward pass. This way we go backward and we just plug this in. This is the backward pass of backprop, which is like the workhorse algorithm of deep learning, going back to at least the 80s. Yeah, so again, in a deep learning setting, this is all very well known. X would be the network input, Y would be the network output, Xi would be the activation within the network at some layer with some index. Fi would be the ith layer, which takes it from this index to just the next index. And the reason why I wrote this down this way is just to illustrate some very nice properties and similarities in structure actually with differential equations. Because differential equations at the very conceptual level actually work very, very similar, where you have f being some initial, x being some initial state, xi, you can think of the solution at some time point, at some time index now, and fi being the time stepper, which takes it from the previous time to the next one. And you can actually compute the derivative of the final state with respect to any intermediate and the very first state with the same rule, with the same, sorry, I don't have this here, with the same reverse mode differentiation chain rule. The only thing you need is the Jacobians for the individual time steppers. And this is one of the things that's written with a lot of domain lingo, if you will, in the first chapter, on why there's such a strong connection between what they're doing here, these universal differential equations, and the automatic differentiation for that. In that paper, they called it, I think, differential programming. And all of these other frameworks that they compare with, PyTorch, TensorFlow, right? They have these tables about how much faster they are because of stuff that I'm gonna allude to in a moment, that they do specifically for dynamical systems. But the really interesting thing to really appreciate here is that there's a lot of structure between like the workhorse ideas of deep learning and that of iteratively numerically solving a differential equation. So just a simple example for Euler. So everything here is the same. I'm just making explicit that the ith layer or the ith time stepper applied to the previous state of the system or the previous layer output. Structurally, it's not so different. It's just the previous state plus h time, some right-hand side of the differential equation. I called it h because we kind of have notation creep already. Usually you would call this f as well. So if you have this kind of simple time stepper system, you can recursively compute the entire trajectory through this way, and you can actually keep gradients of all the states with respect to all previous states if you know the Jacobian for the individual time stepping steps, as we said before. And in the case of forward Euler, this is fairly simple. So the derivative of this with respect to the previous time step is just the identity matrix for this part. And then what you need is you need the Jacobian of the right-hand side of the differential equation. But for this whole case of these universal differential equations, we said that the right-hand side here has to be, which is composed of some black box machine learning model and some non-dynamics, which have to be either in an auto-diff environment or for which you need to manually provide the Jacobians. We already said that we require this to have known partial derivatives. So we do know the full Jacobian for this. So for the simple case of forward Euler, differentiating any point of the solution with respect to any other point of the solution is already given if we can just differentiate the right-hand side. Given how simple forward Euler is, this is actually not so surprising. By this point, you might be asking, all I'm saying all the time is differentiating future states with respect to previous states. But what we really wanted is differentiating any state along the trajectory with respect to parameters. Like network weights, there's a little trick here. We can talk about, you can also just believe me for the moment. You can augment the state with the actual state of the system. So u being our state variable and theta being the parameters of the network weights. And then you define that from any time point, ti minus 1 to the next one, your time stepper, well, it forwards the system state in time, but it just copy pastes the network weights. On a slightly more technical level, what this does is it means that the Jacobian has block structure 2 by 2. So each of these are matrices now. One is just the old derivative of the next time step with respect to the previous time step. And one is actually having the derivative of the output with respect to the parameters. And very quickly, the cool thing, if you multiply 2 of these for neighboring time steps, as you do, if you do the chain rule, one of the blocks is going to track the derivative of current time steps with respect to other states at times which are further and further away. So this is how you differentiate the final state with respect to any intermediate state and even the initial state. And one of the other blocks is actually going to start accumulating the derivatives with respect to the network parameters, which we actually wanted to get out of this. Okay, one slightly more complicated example here, just to show you that it's not so much work actually to get this done in practice, is Runge-Kutta fourth order. So this is just grabbed from my own code base, which is why it has this somewhat cryptic comment on that. Sorry for that. But you might just, if you know Runge-Kutta fourth order, you might already just see from structure. You might just recognize some things. So this is the 2-6 rule. What you do is you get a state at the left side of your integration interval. Just forward it kind of with forward Euler style, and then you plug that in to do a bunch of other explicit forward estimates, and then you average estimates of the change, and then you average them. So what this does is it creates a computational graph because stuff gets plugged into each other. So the Jacobians are going to be a bit more difficult, but the nice thing is in an auto-diff environment like Torch, which keeps track of the Jacobians for every operation that is implemented, you just write this down. Model is going to be the right-hand side of your differential equation. This is going to be the solver for it that does it for one step from ti to ti plus 1. That's the numerical integration. And then you can just ask PyTorch to give you the Jacobian. You don't need to manually keep track of it. So it can be very simple. So everything I've said so far is about explicit methods with fixed time step length. This one of the things that I wanted to get across, that conceptually and getting started with it can actually be quite simple. You don't need to go to neural ODEs, which I think was one of the open questions from the discussion from last time, like how difficult is it to get started with optimizing differential equations, specifically to have good solutions, versus just to have good right-hand sides. I want to close on one maybe more casual note as a warning. In more general cases, it's at some point all of this, fluffy conceptual stuff that I've been talking about starts hitting the reality of actual numerically solving systems. So one thing we've already talked about is this interesting structure of the backward pass that comes out of the chain rule, that you start with the last Jacobian of the last function that you applied, or the last time step solver, if you're talking about the dynamic system. So you're reversing the order of the time steps, you're reversing time, which raises questions about the stability of the time reverse system. And another one is thing to quickly mention is I always talked about fixed step lengths. If you consider variable step lengths, it may be more natural to look at the time continuous version of this. So both of these are called the adjoint method. The discrete time version, for instance, some of you might know from data assimilation, where this plays a role in geophysics. But also the time continuous version exists, where vector is passing through the system from some initial state backward in time. They now have an actually continuous description, and once you're reaching that stage and you need to decide on your own numerical solver just for doing the backward pass, which can actually be different from the forward one, things get to the point where you really need to start thinking a bit more about the details and just writing down a few lines of code of PyTorch as I showed them. And this is maybe where we go back to some of the main claims of this paper here about the universal differential equation, is that it's really good to have someone who has a mature toolbox, who has thought about stuff like stiffness and stabilizing your solutions. So once you start getting to real applications, it's good to have these kind of toolbox around. But if you just want to get going for simple systems, like we had them actually both today and last times, where we have like 32-dimensional systems evolving over time, or fairly easy differential equations this shape last time, I think you can get going quite quickly without needing to have the full framework. Yeah. So that would be it for today. For the second paper, I don't know how many of you are still around. If there's a question, I'm happy to take them.
Shockingly, we haven't lost a single person.
Okay.
That was a great presentation. I really like that. I think you presented this complex topic really nicely. Yeah, I mean, I was also, so let's see, do we have questions in chat right now? Anyone go ahead and ask if anything's not clear. you have any ideas or thoughts. I'm really impressed with the Oceananigans package. The more I look at it, it's very full-featured. It does a lot of great stuff. These fully differentiable methods are really moving along, and probably it's not too long before we'll have something like a general circulation model with a differentiable dynamical core. At the same time, I wonder about this as a software tool. Clearly, for differential equations, Julia is just the best there is. But suppose you want to train your neural network to do this parameterization as they've done, and you want it to do something fancy. You want to do, I don't know, LSTMs and transformers and layer normalization and dropout and all this fancy stuff. Are you going to be able to get that going in Julia? And I'm really not sure how mature the machine learning side of things is there. I don't know if anyone has any experience or thoughts.
Yeah, I also thought, actually, we talked about keeping track of Julia as a tool for machine learning for years, but I think it's fair to say that at this point, doing like more mainstream machine learning is still very exotic to do it in Julia.
Yeah, it's enough of a pain, I think. I mean, this is what I do once a year. I go to their forums, look at the problems people are having. People say, yes, we're working on it. So I think at this point, the gain for the differential equation side has to be really big for you to take the pain of doing machine learning in Julia. But maybe someone will come and correct us. Maybe we'll get some angry emails from the Julia crowd. Who knows?
Yeah, some of the speedups they show in this other table of the paper are actually quite impressive for these differential equation problems.
Any other questions before we wrap up? Okay, thanks everyone for joining. Thanks, Marcel. It was a great presentation, both the mixology part and the technical part after. We will meet again in 2 weeks. Anyone who has an idea for a paper or wants to do a short presentation, just please get in touch. Thanks, everyone.
Bye.
Bye.
Bye.